Close your eyes and imagine a computer that doesn't choose. A machine that explores every possibility at once, that exists in multiple states simultaneously, that harnesses the deepest, strangest rules of reality itself. This isn't science fiction. This is quantum computing. Tonight, let yourself drift through 100 facts about the most profound technology humanity is building. No hype, no fantasy, just the honest, fascinating story of how we're learning to compute with the universe instead of against it. From the scientists who proved it was possible, to the machines being built right now, to the future slowly taking shape in laboratories around the world. Let curiosity guide you. Let wonder relax you. Let these ideas carry you gently, peacefully, towards sleep. 100 quantum computing facts to fall asleep to. Let's begin. There are problems in this universe, problems so vast, so intricately woven into the fabric of reality, that if you asked the most powerful classical computer to solve them, it would need more time than has passed since the beginning of everything. Longer than the age of the universe itself. Just running, calculating, forever reaching toward an answer it would never find. Think about that for a moment. Problems that exist, that we can define, that we can touch with our minds, but that lie forever beyond the reach of ordinary computation. For decades, we built computers faster and faster. Smaller transistors, more processing cores, exponential growth. And yet, there remained this wall. This quiet, immovable boundary at the edge of what classical computing could ever hope to achieve. But then, in 1982, a physicist named Richard Feynman noticed something curious. Something profound. He was thinking about simulating nature, trying to model quantum systems on classical computers, and he realized they couldn't do it efficiently. The numbers grew too large. The possibilities too numerous. Classical machines would drown in the complexity. And Feynman asked a simple question, one that would change everything. If nature doesn't compute classically, if the universe itself operates on quantum principles, then why should we try to simulate it with classical rules? What if we built computers that thought the way nature thinks? This was the seed of an idea, a whisper of possibility. Because quantum computing, and let this settle in gently, quantum computing isn't just a faster computer. It's not about speed. It's not about doing the same things we've always done, only quicker. It's something else entirely. It's a different way of computing reality itself. A way of asking questions in the same language that the universe uses to answer them. A way of stepping through doors that were always locked to us before, not by forcing them open, but by learning that they were never solid to begin with. The universe has been quantum all along, quietly operating on principles that seem impossible, magical even, by the standards of our everyday experience. Particles in two places at once. Information that spans across space instantaneously. Probabilities that interfere with each other like waves in water. And now, slowly, carefully, we're learning to harness that strangeness. To build machines that don't just calculate, but that exist in multiple states, explore multiple paths, and collapse into answers that classical computers could spend eternity searching for. This isn't science fiction. This is happening now. In laboratories around the world. In tech companies and research institutions. Quantum computers are being built. Refined. Tested against problems that have waited patiently for their arrival. And as you drift deeper into rest, let yourself wonder, what becomes possible when we stop computing against the grain of reality and start computing with it? What doors open when we finally learn to speak the universe's native language? So let's talk about how this actually works, in a way that won't jolt you awake, but will let you drift alongside some of the strangest, most beautiful ideas in all of science. First, Forget everything you know about how computers work. Just for a moment. Let it all go. A classical computer, the one you use every day, thinks in bits. Little switches. Each one is either off or on. 0 or 1. Black or white. Every calculation, every decision, is built from millions and millions of these tiny binary choices. And that's perfectly fine for most things. Bits choose. They commit. They land on one side or the other, and the computer marches forward, step by step, down a single path toward an answer. But a qubit, a quantum bit, doesn't choose. Not right away. A qubit exists in possibilities. It holds 0 and 1 at the same time, in a kind of shimmering, probabilistic cloud. It doesn't commit until you ask it to, until you measure it. Until that moment of observation, it remains suspended, hovering, containing multitudes. And this is superposition. Imagine you're standing at a crossroads. In classical computing, you pick a path. You walk down it. You see where it leads. If it's wrong, you backtrack. Try another path. One at a time. Sequential. Patient. But with superposition, you walk down all the paths at once. The qubit explores every possibility simultaneously, like a ghost that can pass through walls, experiencing every route, every outcome, all at the same time. And only when you need an answer, when you finally look, does it collapse into one definite state. This is how quantum computers explore solution spaces that would take classical computers lifetimes to search. Not by being faster at walking down one path, but by walking down every path in parallel, through the quantum magic of existing in multiple states at once. It sounds impossible. It feels impossible. And yet, this is how reality works at the quantum scale. This is what particles do when we're not watching them. But superposition is only the beginning. There's something even stranger. Something that made Einstein himself uncomfortable. Something he called spooky action at a distance. Entanglement. When two qubits become entangled, and listen to this carefully because it shouldn't be possible, but it is. When they become entangled, they form a connection that transcends space itself. You can separate them. Put one qubit here on Earth, send the other to the edge of the galaxy, and they remain connected. Not through any signal. Not through any communication we can detect. But connected nonetheless. If you measure one, the other instantly knows. Instantly responds. No matter how far apart they are. No light speed delay. No message traveling between them. Just instant correlation. As if distance means nothing. As if they're still somehow one thing, even when they're many things. This is the moment where quantum mechanics stops being just weird and becomes almost mystical. Where even the scientists developing these systems pause and feel a sense of awe at what nature permits. Einstein didn't like it. He thought it meant the theory was incomplete. That there must be hidden variables, secret information we weren't seeing. Because surely the universe couldn't work this way. But experiments proved him wrong. Again and again. Entanglement is real. It's been measured, verified, used. And in quantum computers, entanglement is power. It's what allows qubits to work together in ways that classical bits never could. To coordinate their superpositions. To create computational states that represent exponentially more information than the same number of classical bits ever could. Two classical bits can be in one of four states at a time. Two qubits in superposition and entanglement. They can represent all four states simultaneously. 3 qubits. 8 states at once. 10 qubits. Over 1,000 states. 20 qubits. Over 1,000,000. The numbers grow impossibly fast. 50 qubits can represent more states simultaneously than there are atoms in the sun. This is why quantum computers aren't just faster. They are fundamentally different. They operate in a space of possibility that classical computers can't even enter. Now, you might wonder, if qubits are in superposition, in all these states at once, how do we guide them? How do we steer them toward the answers we seek? We use something called quantum gates. And you don't need to understand the mathematics. Just know this: quantum gates are ways we steer probability. We apply them to qubits, and they don't flip switches like in classical computing. Instead, they rotate probabilities. They adjust the angles. They choreograph the interference patterns, guiding the quantum system so that wrong answers cancel out and right answers amplify. It's like conducting an orchestra of probabilities, each instrument playing all possible notes at once, and through careful conducting, through precise timing and interference, you bring them into harmony, into one clear, resonant answer emerging from the quantum noise. These are the strange rules: superposition, entanglement, quantum gates that guide probability itself. Rules that seem impossible, until you remember that this is how the universe has always worked. We're just learning to work with it, instead of around it. For years, quantum computing was theoretical, beautiful mathematics on paper, elegant thought experiments. But thought experiments don't change the world. They don't solve problems. They don't prove anything beyond what's possible in principle. And so there were skeptics. Plenty of them. People who said, sure, it's interesting physics, but can you actually build anything useful? Can you do something a classical computer can't? Then came 1994. A mathematician named Peter Shea, working at Bell Labs, published an algorithm, a quantum algorithm. And when people understood what it could do, everything changed. Shea's algorithm could factor large numbers. Now, you might think, factoring numbers. That doesn't sound revolutionary. It sounds like middle school mathematics. But listen closely to why this matters. All of modern encryption, the security that protects your bank account, your private messages, government secrets, military communications, nearly all of it relies on one simple fact. Factoring large numbers is incredibly hard for classical computers. If I multiply two large prime numbers together, that's easy. Takes milliseconds. But if I give you the result, that huge number, and ask you to find the original primes, to factor it back, your classical computer could run for thousands of years and never find the answer. This isn't a flaw in the computer. It's mathematics. The problem grows exponentially harder as the numbers get bigger. It's what makes encryption secure. The math protects us. But Shea's algorithm, running on a quantum computer, could factor those numbers efficiently. Not in thousands of years. In hours. Maybe minutes. This was the uh-oh moment. Suddenly quantum computing wasn't just academic. It was a threat. A promise. A fundamental shift in what was computationally possible. Governments paid attention. Companies paid attention. Because Shea's algorithm proved that quantum computers, when we build them large enough, will break the encryption that holds the digital world together. Not might. Will. But here's what's important, and why Shea's algorithm matters beyond the threat to encryption: it was proof. Undeniable proof that quantum algorithms could solve certain problems exponentially faster than any classical algorithm ever could. The skeptics had their answer. 2 years later, in 1996, another algorithm emerged. Love Grover, working at the same Bell Labs, discovered something different. Something more subtle. Grover's algorithm searches unsorted databases. Imagine you have 1 million items scattered randomly, and you need to find one specific item. Classically, on average, you'd have to check half of them. 500,000 searches. Grover's algorithm could do it in about 1,000. Not exponentially faster. Quadratically faster. The square root of the number of items. And this matters, this really matters, because it shows the limits. It shows that quantum computers aren't magic. They don't make everything instantly fast. Some problems, they can only speed up a little. Some problems, they can't speed up at all. Grover's algorithm was important not because it was the most powerful quantum algorithm, but because it was honest. It showed where quantum advantage begins and ends. It separated the real promise from the hype. And the scientific community respected that. It made quantum computing more credible, not less. Because real science acknowledges limits. But algorithms on paper, even groundbreaking ones, still aren't physical reality. The question remained, could anyone actually build a quantum computer that worked? That did something, anything, that proved the concept in hardware? The late 1990s and early 2000s became a race. Not a loud, public race. A quiet one. In university labs. In research institutions. Scientists trying to coax qubits into existence. Trying to make them stable enough to compute. Trying to entangle them. Control them. Read them. It was extraordinarily difficult. Qubits are fragile. Unimaginably fragile. The slightest vibration, the tiniest temperature fluctuation, even stray electromagnetic fields, can destroy their quantum state. Can collapse their superposition before you finish computing. This is called decoherence. And it was, and still is, the greatest enemy of quantum computing. But slowly, carefully, breakthroughs came. In 1995, a group at NIST, the National Institute of Standards and Technology, demonstrated the first quantum logic gate. An actual physical operation on an actual qubit. Not perfect. Not practical yet. But real. Then in 2001, a team at IBM and Stanford did something remarkable. They used 7 qubits, 7 carefully controlled nuclear spins in molecules, to run Schia's algorithm. And they factored the number 15. 15. 3 times 5. Now, you might smile at that. 15 seems trivial. A child could factor 15 in seconds without any computer at all. And that's fair. It was a tiny demonstration. But it was undeniable. Those 7 qubits existed in superposition. They became entangled. Quantum gates guided their probability amplitudes. And they performed a computation, a genuinely quantum computation, that demonstrated the principles of Schia's algorithm working in physical reality. Not theory. Not simulation. Reality. The number 15 was factored by a quantum computer, and that small, humble achievement was proof that this wasn't fantasy. That the strange rules of quantum mechanics could be harnessed, controlled, directed toward computation. These were the breakthrough moments. Schia showing what was possible, Grover showing what was realistic, and those early experimentalists, working with handfuls of qubits, showing that it was real. Not easy, not solved, not ready to change the world yet, but real. The door had opened, and scientists around the world could see through it, could see the path forward, difficult as it was, toward machines that might one day compute the impossible. The skeptics hadn't disappeared, but they had to reckon with evidence, with algorithms that worked, with qubits that computed. Quantum computing had crossed the threshold from dream to engineering challenge. And engineering challenges, given enough time, given enough brilliant minds working on them, can be solved. Something shifted in the early 2000s. Quantum computing stopped being purely academic. It started becoming something else, something tangible, something you could visit, touch, invest in. The question was no longer, is this possible? but rather, how do we actually build this? And in 2011, a company called D-Wave made a bold claim. They had built a quantum computer, not a lab experiment, not a research prototype, a commercial quantum computer, one you could buy. The scientific community was skeptical, intensely skeptical, because D-Wave's machine didn't work like the universal quantum computers Shea and Grover had envisioned. It used something called quantum annealing, a specialized approach designed for optimization problems, for finding the lowest energy state in a complex landscape of possibilities. It couldn't run Shea's algorithm, couldn't factor numbers, couldn't do many of the things people expected quantum computers to do. Was it really quantum computing? The debate raged for years. Papers were published. Tests were run. Some showed modest speed-ups. Others showed none. The questions persisted. Was it using quantum effects meaningfully? Or was it just a very cold, very expensive classical computer? But here's what mattered, regardless of the controversy. D-Wave did something no one else had done. They made quantum computing commercial. Real. Something companies could purchase and experiment with. Lockheed Martin bought one. Google bought one. NASA bought time on one. Suddenly, quantum computing wasn't confined to university labs. It was in the world. Imperfect, controversial, limited, but undeniably present. D-Wave forced the conversation forward. They made skeptics defend classical computing's advantages. They made believers prove quantum advantages. And in that friction, in that pressure, the field advanced. But the question remained, could anyone build a universal quantum computer that definitively, unquestionably, did something no classical computer could match? October 2019. Google announced something they called quantum supremacy. They'd built a quantum processor, a chip of superconducting qubits they named Sycamore, 53 qubits arranged in a carefully designed architecture. And they gave it a task. A very specific, very strange task. Not a practical problem. Not factoring numbers or breaking encryption. Just a sampling problem. A computational task designed to be hard for classical computers but natural for quantum systems. Their quantum processor completed it in 200 seconds. They estimated the best classical supercomputer in the world would need 10,000 years. Now, IBM immediately pushed back. Said that with clever algorithms, a classical computer could do it in days, not millennia. The number wasn't 10,000 years. Maybe just a few days. But even if IBM was right, even if it was days instead of millennia, that's still a quantum computer doing in minutes what takes classical systems days. That's still supremacy. That's still a threshold crossed. For the first time, undeniably, a quantum computer had outperformed classical computing on a specific task. Not a simulation. Not an approximation. An actual computation where quantum mechanics gave a genuine advantage. The era of will it ever work was over. The era of how do we make it work better had begun. And here's where the story becomes even more interesting. Because there isn't one path forward. There isn't one type of quantum computer winning the race. There are multiple approaches. Multiple hardware platforms. Each with different advantages, different challenges, different believers. Superconducting qubits, like Google's Sycamore, and IBM's quantum processors. These use circuits cooled to nearly absolute zero, where electrical currents flow without resistance, and quantum states can be controlled with microwave pulses. They're fast. They're relatively easy to fabricate with existing chip manufacturing techniques. But they're fragile. They decohere quickly. They need to stay impossibly cold. Then there are trapped ions. Individual atoms, held in place by electromagnetic fields, manipulated with laser pulses. These qubits are incredibly stable, incredibly precise. They can stay coherent much longer than superconducting qubits. Companies like IonQ are building machines this way. But they're slower, harder to scale to thousands of qubits. Each ion needs its own laser control system. Photonic quantum computers use particles of light, photons, as qubits. They can operate at room temperature. They can potentially network quantum computers together through optical fibers. Companies like Xanadu and PsiQuantum are betting on this approach. But detecting and manipulating single photons is extraordinarily difficult. The error rates are challenging. Neutral atoms, another approach, where hundreds or thousands of atoms are trapped in optical lattices, held by intersecting laser beams. Companies and research groups are showing this might scale beautifully, might offer the best of multiple worlds. But it's newer, less developed. And silicon spin qubits, using the same silicon technology that powers every computer chip, but manipulating the quantum spin of individual electrons. This might allow quantum computers to be manufactured in existing chip foundries, might make them smaller, cheaper, more accessible. Intel is exploring this. Academic groups are racing ahead. But it's technically demanding in entirely different ways. No one knows which approach will win. Perhaps none of them win alone. Perhaps different quantum computers, built on different platforms, will solve different kinds of problems. Perhaps we'll have quantum computing ecosystems, hybrid systems, where superconducting processors handle some tasks, trapped ions handle others, photonic systems network them together. Or perhaps one approach will suddenly break through. We'll solve the decoherence problem. We'll scale to millions of qubits. And will become the standard. The way silicon transistors became the standard for classical computing. Right now, in laboratories and companies around the world, brilliant teams are working on every approach. Competing, collaborating, publishing, protecting trade secrets. Racing toward stability, toward scale, toward the quantum computers that will actually change the world. What we know is this: it's happening. The machines exist. They compute. They demonstrate advantage on specific problems. The engineering challenges are being solved, one qubit at a time, one error correction code at a time, one breakthrough at a time. We've crossed from if to when and how. And that's, when you really think about it, extraordinary. The future isn't written yet. The winner isn't chosen. But the race is real, and the finish line, wherever it is getting closer. So, quantum computers exist. They're being built, improved, tested. But you might wonder, what are they actually for? Beyond breaking encryption, beyond abstract mathematics, what problems will they solve that matter to everyday life? The answer is emerging slowly, carefully, without the hype that sometimes surrounds new technology. Because the scientists and engineers working on this, they've learned to be cautious, to be honest about timelines, to separate what's possible now from what's possible eventually, from what might never be possible at all. But there are areas, specific domains, where quantum computers are starting to show early advantage, where the strange rules of superposition and entanglement align perfectly with the structure of real-world problems. Let's talk about a few of them. First, optimization. The world runs on optimization problems. Questions that ask, what's the best way to do this? The most efficient route? The lowest cost? The highest return? Imagine you're a logistics company. You have thousands of delivery trucks, millions of packages, constantly changing traffic patterns, weather delays, customer preferences, vehicle maintenance schedules, Fuel costs. What's the optimal route for each truck? The optimal loading pattern. The optimal timing. Classical computers tackle this by trying possibilities, testing routes, comparing outcomes. They use clever algorithms, shortcuts, approximations, and they find pretty good solutions. Good enough solutions. But pretty good costs money. Every extra mile driven, every delayed delivery, every suboptimal choice, multiplied across thousands of trucks and millions of deliveries, adds up to billions of dollars in inefficiency. Quantum computers, with their ability to explore multiple possibilities simultaneously through superposition, might find better solutions. Not perfect solutions. Optimization problems are still hard even for quantum systems, but measurably better. Meaningfully better. Companies like Volkswagen have been testing quantum algorithms for traffic flow optimization, DHL for logistics routing, financial institutions for portfolio optimization, trying to balance risk and return across thousands of investment options simultaneously. The results so far are modest. Early, but they're real. A few percentage points of improvement in routing efficiency. Slightly better portfolio allocations. Faster detection of anomalous patterns that might indicate fraud. Not revolutionary yet, but pointing toward something. Toward a future where quantum computers handle the optimization problems that cost industries billions and find solutions classical computers miss. Then there's chemistry. And this is where quantum computers feel almost inevitable. Where the match between problem and tool seems perfect. Because molecules are quantum. Every chemical reaction, every bond between atoms, every electron orbiting every nucleus, it all follows quantum mechanics. The same strange rules that make quantum computers possible: superposition, entanglement, probability amplitudes. These are the rules that govern chemistry itself. And classical computers struggle with chemistry. They can simulate small molecules, simple reactions. But as molecules get larger, as you add more atoms, more electrons, the complexity explodes exponentially. A molecule with just a few dozen atoms, interacting quantum mechanically, creates a problem space so vast that no classical computer can fully simulate it. So we use approximations, shortcuts. We get close, but we miss details. We miss rare configurations that might matter. We miss the subtle quantum effects that determine whether a drug works or fails. Quantum computers could simulate molecules naturally, directly, using qubits to represent quantum states, letting superposition mirror the actual quantum behavior of electrons. This is already beginning. Small demonstrations. IBM and Daimler simulating lithium hydride molecules for battery research. Google simulating chemical reactions. Academic groups modeling enzyme catalysis. The molecules are still tiny. The simulations still limited. But the principle works. And the implications, if this scales, are profound. Drug discovery currently takes over a decade and billions of dollars. Much of that time is spent testing compounds, trying to predict how molecules will behave in the body, how they'll bind to proteins, what side effects they might cause. Quantum simulations could accelerate this. Could let researchers test thousands of candidate molecules virtually, understanding their quantum behavior precisely, before ever synthesizing them in a lab. New antibiotics for resistant bacteria. Better cancer therapies. Treatments for diseases we can't currently touch. Not tomorrow. Not next year. But eventually, as quantum computers scale, this becomes possible. And then there's materials science. Energy. Climate. We need better batteries. Much better. Batteries that store more energy, charge faster, last longer. Use abundant materials instead of rare ones. The kind of batteries that make electric vehicles practical for everyone. That make renewable energy reliable when the sun isn't shining and the wind isn't blowing. But designing better batteries means understanding materials at the quantum level. How lithium ions move through crystalline structures. How electrons transfer at interfaces. How materials degrade over thousands of charge cycles. Quantum computers could model these materials. Could help researchers discover new battery chemistries. New catalysts for splitting water into hydrogen fuel. New materials for capturing carbon dioxide from the atmosphere. The same for solar panels. For superconductors. For any technology where quantum effects at the atomic level determine macroscopic performance. And climate modeling, perhaps one of the most important challenges we face, involves simulating quantum mechanical processes. How molecules in the atmosphere absorb and emit radiation. How aerosols form and influence cloud behavior. How chemistry and physics interact across scales from atoms to the entire planet. Quantum computers won't replace classical climate models, but they might enhance them. Might handle the quantum mechanical pieces more accurately. Might help us understand feedback loops we're currently missing. Now, listen carefully to what I'm not saying. I'm not saying quantum computers will solve climate change, or cure all diseases, or make everything optimally efficient overnight. These are hard problems. Quantum computing is one tool. A powerful tool, potentially, but still just a tool. And the quantum computers we have today, they're research instruments. Prototypes. They have dozens or hundreds of qubits when we'll likely need thousands or millions for truly transformative applications. Error rates are still too high. Coherence times still too short. We're still learning how to program them effectively. Still discovering which problems they're actually good at. But the early advantage is there. The proof of concept is there. Industries are investing, not because quantum computers are ready now, but because they can see the trajectory. They can see where this leads if the engineering challenges get solved. If error correction works. If systems scale. And so they're preparing. Learning. Experimenting. Running small problems on today's quantum computers while training their researchers. Developing their algorithms. Positioning themselves for the moment when quantum advantage becomes quantum utility. The revolution isn't here yet. But the foundation is being laid. Problem by problem. Industry by industry. Quantum computer by quantum computer. And that's enough, for now, to keep the world watching. To keep the scientists working. To keep the possibilities growing. Now, let's talk about why this is so hard. Because if quantum computing sounds too good to be true, like it should have already transformed everything, there's a reason it hasn't. The physics is real. The algorithms are proven. The potential is genuine. But building a useful, reliable, large-scale quantum computer is one of the most difficult engineering challenges humanity has ever attempted. Let's be honest about why. First, there's decoherence. Remember how qubits exist in superposition? How they hold multiple states simultaneously. How entanglement lets them coordinate across space. All of that delicate quantum magic, is extraordinarily fragile. A qubit doesn't want to stay quantum. The universe, in a sense, doesn't want it to stay in superposition. Every interaction with the environment, every stray photon, every thermal vibration, every microscopic magnetic field fluctuation, tries to collapse that quantum state, tries to force the qubit to choose, to become classical. This is decoherence. And it happens fast. Unimaginably fast. For superconducting qubits, the ones Google and IBM use, coherence times are measured in microseconds. Millionths of a second. You have maybe 100 microseconds, maybe a few hundred if you're lucky, before the quantum information degrades into noise. That's not long. That's barely enough time to perform a handful of quantum operations before everything falls apart. Trapped ion qubits do better. Much better. They can maintain coherence for seconds, sometimes minutes in the best laboratory conditions. But even seconds, when you need to perform millions of operations to solve a complex problem, even seconds aren't enough. And here's the cruel mathematics. Every operation you perform on a qubit, every quantum gate, introduces errors. Small errors. Tiny imperfections. One operation might have a 99% success rate. Sounds good. But if you need to do 10,000 operations, those errors multiply, compound, accumulate. By the end of your computation, if you haven't corrected those errors, your answer is garbage. Random noise pretending to be a solution. This is why error correction is everything. Classical computers have error correction too. Cosmic rays flip bits. Heat causes glitches. But classical error correction is straightforward. You can copy information, check it, fix it. The errors are random and independent. Quantum error correction is vastly more complicated. You can't copy quantum information. That's a fundamental law of quantum mechanics. You can't just make a backup of a qubit state. Instead, you have to encode one logical qubit, one reliable qubit that you actually compute with across many physical qubits. Maybe 10, maybe 100, maybe 1,000 physical qubits for every single logical qubit you need. You entangle them in specific patterns. You constantly measure them, not the quantum information itself, but the relationships between qubits, detecting when errors occur without collapsing the superposition. You correct the errors in real time while the computation runs. It's astonishingly complex, and it requires the physical qubits to be good enough, stable enough, that the error correction helps more than it hurts. We're not there yet. Not quite. We're close. Tantalizingly close. Groups have demonstrated small error-corrected logical qubits, shown that adding more physical qubits does improve reliability. But we need orders of magnitude more. Thousands of physical qubits working together, with low enough error rates, to create a handful of truly reliable logical qubits. And to run Schia's algorithm on encryption-level numbers. To simulate complex molecules. To solve real optimization problems, we'll need millions of physical qubits. Tens of millions perhaps. We have hundreds today. Hundreds. And then there's the temperature problem. Many quantum computers, the superconducting ones, need to operate at temperatures near absolute zero. We're talking 15 millikelvin. That's 15 thousandths of a degree above the coldest temperature possible in the universe. Colder than outer space. Colder than anywhere in nature. Cold enough that atoms barely move. Achieving this requires dilution refrigerators. Massive machines. Layers of cooling. Intricate plumbing. Weeks to cool down from room temperature. Massive energy consumption just to maintain the cold. And you can't just refrigerate one qubit. You need the entire quantum processor. All the control electronics you can fit at that temperature. All the wiring, carefully designed to minimize heat, while still letting signals in and out. These machines are expensive. Finicky. They break. They warm up accidentally. A single speck of dust in the wrong place, a tiny vibration from a truck passing outside, can ruin everything. Trapped ion systems don't need to be quite so cold. Photonic systems might work at room temperature eventually. But every approach has its own nightmare engineering challenges. Trapping individual atoms with lasers. Keeping them isolated from every stray electromagnetic field. Detecting single photons with near-perfect efficiency. Building optical circuits at the nanometer scale. There's no easy path. Every approach trades one set of problems for another. And here's the scaling reality check. Building 1 qubit. Hard, but doable. Building 10. You're a research group with a publication. Building 100. You're Google or IBM with a serious engineering team. Building 1,000. You're at the edge of what's currently possible. Building 1,000,000. Nobody knows how yet. Every additional qubit adds noise to the system, adds complexity to the control, adds crosstalk, where operations on one qubit accidentally affect its neighbors, adds wiring, control lines, readout systems. The engineering doesn't scale linearly. It gets harder, exponentially harder. You can't just build bigger versions of what works at small scale. This is why there are multiple hardware approaches. Why companies are trying different qubit types, different architectures, modular systems where many small quantum processors link together, new materials, new control schemes, because nobody's sure what will work at the scale needed for truly useful quantum computing. So why am I telling you all this? Why emphasize the difficulty, the problems, the limitations? Because honesty matters. Because quantum computing is real, but it's not magic. It's not right around the corner. It's not going to solve every problem or replace classical computers or change everything next year. It's hard. Brutally hard. The kind of hard that requires decades of work, billions in investment, thousands of brilliant scientists and engineers, slowly, patiently, solving problem after problem after problem. And maybe it won't work. Maybe the engineering challenges are insurmountable. Maybe we'll hit a wall we can't get past. Maybe quantum computers will remain small, specialized tools for specific tasks, never achieving the grand visions people dream about. But I don't think so. Because the progress is real. Coherence times are improving. Error rates are dropping. Systems are scaling. Error correction is beginning to work. It's slow. It's incremental. It's frustrating to people who want instant breakthroughs. But it's happening. The hard truth is that quantum computing is one of the most challenging things we've ever tried to build. The hopeful truth is that we're building it anyway. One qubit at a time. One error correction code at a time. One breakthrough at a time. And that's, perhaps, exactly how something this profound should emerge. Slowly, carefully, honestly, with our eyes open to both the promise and the difficulty. So where are we, really, right now? Not in the hype. Not in the distant future. But here, today, in laboratories and data centers, in research papers and software repositories, in the actual work happening while the world sleeps. The reality is quieter than you might expect. More practical. More hybrid. Because here's what's actually working. Quantum computers don't work alone yet. The most promising applications, the ones showing real results today, use hybrid quantum classical systems. They split the work. Let each type of computer do what it does best. The classical computer handles the heavy lifting, the data management, the optimization of parameters, the orchestration of the workflow. All the things classical computers are already excellent at. And then, for specific subroutines, for particular calculations where quantum effects provide advantage, the classical computer hands off to the quantum processor. Lets it explore that possibility space. Perform that quantum simulation. Sample that probability distribution. The quantum computer does its work, returns results, and the classical computer interprets them, adjusts parameters, sends the quantum processor back for another iteration. Back and forth. Classical and quantum. Working together. This is called the variational approach. And it's how most real quantum computing happens right now. Companies aren't running entire algorithms on quantum processors. They're embedding quantum subroutines inside classical workflows, using quantum computers as specialized accelerators, the way we use GPUs for graphics or machine learning. The quantum part might run for seconds, the classical part for hours. But together, they solve problems neither could handle alone. At least not efficiently. Optimization problems work this way. Some chemistry simulations. Machine learning research exploring quantum-enhanced neural networks. It's early. It's experimental. But it's real work. Real results. Published. Peer-reviewed. Reproducible. And here's something remarkable. You can use these quantum computers yourself. Right now. Today. IBM offers quantum processors through the cloud. You can write quantum circuits in their development environment, submit jobs, and run actual quantum computations on real quantum hardware sitting in their data centers. Google has made some of their quantum processors available to researchers. Amazon has Bracket, a service that gives you access to quantum computers from multiple vendors. Microsoft has Azure Quantum, all accessible through standard cloud interfaces. This is Quantum as a Service, QoS, and it's changing how quantum computing develops. Because now, a graduate student in India, a startup in Brazil, a researcher anywhere with an internet connection, can experiment with quantum algorithms, can test ideas, can contribute to the field without needing a dilution refrigerator and $10 million in equipment. The quantum computers available through these services are still small, still noisy, still limited. You're not going to break encryption or simulate complex molecules on them. Not yet. But you can learn, experiment, develop algorithms, build intuition, prepare for the quantum computers that are coming. Universities are teaching quantum computing courses where students run code on real quantum hardware. Companies are training their researchers. Hobbyists are exploring. The quantum computing community is growing, not just among elite physics labs, but distributed, global, collaborative. And while researchers experiment with hybrid systems and cloud access, governments and security agencies are preparing for something else. The cryptographic threat. Remember Schiess algorithm? The one that can factor large numbers and break encryption. It doesn't work on today's quantum computers. Not even close. You'd need thousands of error-corrected logical qubits. Millions of physical qubits. Extremely low error rates. Systems that are probably still a decade or more away. But, and this is critical, encrypted data can be stored forever. Intelligence agencies know this. Companies know this. Anyone who understands cryptography knows this. If you intercept encrypted communications today, even though you can't decrypt them now, you can store them. Wait. And when quantum computers are powerful enough, decrypt them then. This is called harvest now, decrypt later. And it's not paranoia. It's rational. If you're a nation-state adversary, why wouldn't you collect everything you can now? Medical records, financial data, government communications, corporate secrets, everything encrypted with current standards. Wait 10 years, 15 years. However long it takes, then decrypt it all at once. Suddenly information that seemed safe, private, protected by mathematics, becomes readable, vulnerable, exposed. This is why there's a rush, a quiet, urgent rush, to develop post-quantum cryptography, new encryption algorithms, based on mathematical problems that even quantum computers can't solve efficiently. Problems like lattice-based cryptography, hash-based signatures, multivariate equations. Problems where no quantum algorithm, not even ones we haven't discovered yet, provides exponential speed-up. NIST, the National Institute of Standards and Technology, ran a competition. Years of research, dozens of candidate algorithms, testing, breaking, stress testing, and in 2022, they announced the winners. The new standards. Now comes the hard part, actually deploying them. Every bank, every government agency, every company handling sensitive data, they need to upgrade their encryption, replace their algorithms, update their systems. This takes time, years, maybe a decade, and it needs to happen before quantum computers are powerful enough to break current encryption. It's a race in slow motion, the threat arriving gradually, but inevitably. So this is the quiet present. Researchers running hybrid algorithms on small quantum processors. Students learning quantum programming through cloud access. Security experts upgrading cryptography before the threat fully materializes. No dramatic breakthroughs this week. No sudden revolutions. Just steady work. Incremental progress. Preparation. The quantum computers get slightly better each year. Error rates drop a bit. Coherence times extend. New qubits come online. Error correction demonstrations improve. The algorithms get more sophisticated. The software tools mature. The developer community grows. The cryptographic standards update. Systems begin the slow migration to post-quantum security. It's not exciting in the way sudden breakthroughs are exciting. But it's real. It's happening. It's the actual work of bringing quantum computing from laboratory curiosity to practical tool. And maybe that's appropriate. Maybe the most profound technologies don't arrive all at once. Don't announce themselves with fanfare. Maybe they emerge slowly, quietly, through the accumulated work of thousands of people, each solving small problems, each contributing incremental progress, until one day, without anyone quite noticing when it happened, the impossible becomes possible, the future becomes present, and the work continues. This is where we are, not at the beginning, not at the end, somewhere in the middle of something profound. Let's step back now, away from the qubits and the algorithms, away from the technical details, and ask a different kind of question. What does this mean for us? For society? For the way power and knowledge and security are distributed in the world? Because technology is never just technology. It reshapes lives, shifts balances, creates winners and losers. And quantum computing, when it arrives at scale, will reshape things in ways we're only beginning to understand. First, there's the security question. We talked about encryption earlier. How Schia's algorithm threatens it. How post-quantum cryptography is being developed. But let's think about what that really means, in human terms. Right now, your private conversations, your medical records, your financial transactions, all of it relies on mathematical problems being hard to solve, on the assumption that certain calculations would take longer than the age of the universe. That assumption has held for decades. We've built our digital infrastructure on it. Our trust, our privacy, our security, and that assumption, eventually, will break. Not today, not tomorrow, but someday. Maybe in 10 years. Maybe 15. Maybe sooner than we expect if there's a breakthrough. When it does, every system still using old encryption becomes vulnerable. Every stored communication, every archived database, every backup sitting on a server somewhere. Nations are preparing. Companies are preparing. But what about smaller organizations? What about the systems we've forgotten about? The medical devices, the industrial controllers, the embedded systems that were never designed to be updated. There's a long tail of vulnerability, and we don't know how long it will take to protect everything that needs protecting. This isn't meant to create fear. It's meant to create urgency. The transition to post-quantum cryptography isn't optional. It's not something we can postpone. It's infrastructure work, unglamorous, but essential. Like replacing old bridges before they collapse. Except we don't know exactly when the weight limit will be exceeded. And then there's the question of access. Of who gets to use this technology. Who benefits from it? Quantum computers are expensive. Extraordinarily expensive. The dilution refrigerators alone cost hundreds of thousands of dollars. The full systems, millions. The expertise to operate them, rare and valuable. Right now, only a handful of countries have serious quantum computing programs. Only a handful of companies can afford to build them. Only elite universities have the resources to contribute meaningful research. And as quantum computing matures, as it begins to provide real advantages in drug discovery, materials science, optimization, financial modeling, those advantages will accrue to whoever has access. The company that can simulate molecules quantum mechanically discovers better drugs faster. The nation that can optimize its logistics saves billions. The financial institution that can process quantum-enhanced algorithms makes better predictions. The digital divide, already significant, could become a quantum divide. Between nations that have the technology and nations that don't. Between companies with quantum access and companies without. Between institutions that can afford the talent and infrastructure, and those that can't. Cloud access helps. Quantum as a service democratizes somewhat. A researcher anywhere can run experiments now. That's genuinely important. But the most powerful quantum computers, the ones with thousands of error-corrected qubits, will they be freely accessible? Or will they be strategic assets? Controlled, protected, used for competitive advantage? History suggests technology concentrates before it democratizes. Early computers filled entire buildings and only governments could afford them. Now they're in every pocket. Perhaps quantum computers will follow the same path. Perhaps not. Perhaps the physics demands they remain centralized, accessible only through cloud services. Never quite personal, never quite democratized. We don't know yet. But the question matters. And then, there's the geopolitical dimension. Nations understand what's at stake. China is investing billions in quantum research. Has launched quantum communication satellites. Is building quantum computing centers. The United States has declared quantum computing a national priority. The National Quantum Initiative. Export controls on quantum technology. Restrictions on who can access certain research. The European Union has quantum flagships. Major funding initiatives. Collaboration between countries trying to remain competitive. It's not quite a race, not in the space race sense, but there's definitely competition. National pride. Strategic concerns. The belief that quantum supremacy, real, sustained quantum advantage, could shift global power. Because quantum computing isn't just about faster calculations. It's about cryptography. About simulation of nuclear weapons without testing. About optimization of logistics and supply chains. About materials science that enables better batteries, better solar panels, better everything. The nation that leads in quantum computing gains advantages across multiple domains: economic, military, scientific. And so there are talent wars. Countries competing for the relatively small pool of quantum researchers. Universities recruiting. Companies offering huge salaries. Researchers becoming strategic assets themselves. Export controls tightening. Technology transfers scrutinized. International collaboration, traditionally the bedrock of science, now complicated by national security concerns. Chinese researchers publish groundbreaking papers, and American researchers wonder if they should cite them, collaborate with them, or if doing so might jeopardize their own funding, their security clearances. It's messy, complicated. There's no clear right answer. Science benefits from openness, from collaboration, from the free exchange of ideas. But nations have legitimate security concerns, real strategic interests, and quantum computing sits at that intersection. Too important to ignore, too powerful to share freely. And somewhere in all of this are people. Graduate students choosing quantum physics, knowing their career might take them into classified work, might prevent them from publishing freely, might make their research a matter of national security. Engineers deciding which company to join, which quantum computing approach to bet their career on, knowing that some paths lead to breakthroughs and recognition, while others lead to dead ends and obsolescence. Ethicists wondering how to guide the development of technology this powerful, how to ensure it benefits humanity broadly, not just the wealthy, not just the powerful. Policymakers trying to write regulations for technology they barely understand, trying to balance innovation with security, competition with collaboration, national interest with global progress. These are the human consequences, the ripples beyond the technology itself. And they matter just as much as the qubits and the error rates and the algorithms. Because technology shapes society. But society also shapes how technology develops. Who has access? What problems get solved? Whose interests are served? Quantum computing will be powerful, transformative, potentially. But transformation is never neutral. It always creates winners and losers. Always raises questions about fairness, access, control. We're early enough, still early enough, to think carefully about these questions, to make choices, to shape the development of quantum computing in ways that serve broader human flourishing, not just narrow interests. Whether we will, remains to be seen. The technology advances. The qubits improve. The algorithms mature. But the human questions, the questions about security and access and power, those remain open, waiting for answers we haven't yet given, waiting for choices we haven't yet made. The future isn't just technical, it's human, and it's still being written. So, what happens next? Not in science fiction, not in the breathless predictions of people trying to sell something, but in reality, based on where we are, where the physics leads, where the engineering seems headed. Let's talk about the future. Carefully, honestly. If you ask quantum computing researchers, the ones actually building these systems, when they expect to have fault-tolerant quantum computers, machines with enough error-corrected logical qubits to solve genuinely useful problems, most will say the same thing. The 2030s. Maybe. Not next year. Not in 5 years. The 2030s. That's the realistic timeline for quantum computers that can run Schiess algorithm on real encryption. That can simulate complex molecules accurately. That can tackle optimization problems classical computers genuinely can't handle. A decade away. Perhaps longer. Perhaps a bit sooner if there are breakthroughs. But here's the uncertainty, the honest uncertainty. Nobody knows for sure. We know error correction works in principle. We've demonstrated it on small scales. But scaling to thousands, tens of thousands, millions of physical qubits, all working together, all maintaining coherence, all correcting errors faster than new errors appear. That's still an open engineering challenge. A hard one. Companies have roadmaps. IBM plans to have thousands of qubits by the late 20s. Google has timelines. Amazon, Microsoft, IonQ, Rigetti, everyone building quantum computers has plans. But plans meet reality. Reality pushes back. Unexpected problems emerge. Solutions take longer than expected. Or, breakthroughs happen. Someone discovers a better qubit design, a better error correction code, a better way to control thousands of qubits simultaneously. And suddenly the timeline accelerates. We don't know. Can't know. This is still research. Still development. Still pushing against the boundaries of what's physically possible. The 2030s is an educated guess. Not a promise. Not a guarantee. Maybe. But let's say it happens. Let's say by 2035, fault-tolerant quantum computers exist. Useful ones. Accessible ones. What changes? Everything. No, not everything. And this is important. This is where we separate reality from hype. Quantum computers won't replace classical computers. Won't make them obsolete. Won't suddenly make every computation faster. Most things you do on a computer, sending email, browsing websites, editing documents, watching videos, playing games, classical computers handle perfectly well. Quantum computers offer no advantage. None. Quantum computers are slow at many things. They excel at specific types of problems. Problems with particular mathematical structures. Problems where quantum effects, superposition, entanglement, interference, can be leveraged. But for sequential tasks, for logic, for the kind of step-by-step processing that most software does, classical computers are better, faster, more efficient, more reliable. Quantum computers won't be in your laptop. Probably ever. The physics doesn't work that way. The engineering doesn't support it. There'll be specialized machines. Resources you access when needed. Like supercomputers today. Like cloud computing today. You won't own one. You'll use one when the problem demands it. And many problems people hope quantum computers will solve, they won't. Quantum computers won't make artificial intelligence suddenly conscious. Won't solve NP-complete problems in polynomial time. Won't break all cryptography, only certain types. Won't violate the fundamental limits of computation. They're bound by the same laws of physics. The same information theoretic limits. They're just bound differently. Some problems that are hard for classical computers remain hard for quantum computers. Some problems, even with quantum mechanics on your side, are still exponentially difficult. Quantum computing isn't magic. It's different physics, different rules, but still rules, still limits. But here's what is true. Here's what matters. Quantum computers change which problems are solvable. Not just how fast we solve them, which ones we can solve at all. There are problems right now that would take classical computers billions of years, that quantum computers could solve in hours, days, weeks. That's not a speed improvement. That's a categorical change. The difference between impossible and possible. Simulating large molecules accurately. Understanding protein folding from first principles. Optimizing systems with millions of interacting variables. Certain machine learning tasks. Certain types of searches through enormous datasets. These problems, currently locked behind computational barriers so high we can't even approach them, might become accessible. And we don't fully know what that enables. What discoveries become possible. What technologies emerge? What questions we can finally answer? Because the history of computing isn't just about doing old things faster. It's about doing entirely new things. Things that were unimaginable before the tools existed. No one predicted social media when the first computers were built. No one predicted machine learning would revolutionize image recognition. No one predicted the internet would reshape human communication. The tools came first. The applications emerged later, often in surprising ways. Quantum computing will likely follow the same pattern. We have ideas now. Drug discovery, materials science, optimization, cryptography. But the real applications, the ones that change everything, might be things we haven't imagined yet. Problems we haven't thought to ask. Discoveries we haven't anticipated. So the future isn't certain, isn't guaranteed, isn't arriving on a predictable schedule. But it's coming. Slowly, incrementally, through the accumulated work of thousands of researchers, billions in investment, decades of patient effort, fault-tolerant quantum computers, probably in the 2030s, maybe sooner, maybe later, applications in chemistry, materials science, optimization, emerging as the machines improve, as algorithms mature, as we learn which problems quantum computers actually excel at. A quantum internet, perhaps, where entanglement allows unhackable communication, where quantum sensors detect things classical sensors miss. A world where some problems, the right problems, become solvable in ways they never were before. Not a revolution overnight. Not a sudden transformation. But a shift. A gradual opening of doors that were closed. A slow expansion of what's computationally possible. And maybe that's enough. Maybe the future doesn't need to be grandiose to be profound. Maybe quantum computing doesn't need to solve everything to be worth pursuing. Maybe it's enough that it solves some things. Important things. Impossible things. Maybe it's enough that we're learning to compute with the universe instead of against it. Maybe it's enough that the impossible, slowly, carefully, becomes possible. The qubits will improve. The error rates will drop. The systems will scale. Or they won't. Not as much as we hope. Not as fast as we want. But either way, we're learning. We're trying. We're pushing against the boundaries of what matter and energy and information can do. And that journey, that patient, difficult, uncertain journey, is already changing us. Already teaching us. Already showing us new ways to think about computation, about reality, about what's possible when you stop fighting the strangeness of the universe and start working with it. The future is uncertain, but it's being built, one qubit at a time. And so, we've journeyed through the quantum world together. From Feynman's insight to the machines being built today. 100 facts about computing at the edge of reality. If these ideas brought you peace tonight, if they carried you gently toward rest, please subscribe to this channel for more long, calming explorations like this one. The qubits continue evolving. The future unfolds quietly. But you can rest now. Thank you for exploring quantum computing with us. Sleep well, and good night.